So we are in chapter 16. Towards the end of the previous lecture, I explained to you the parameterization of a surface. A curve in 3D is parameterized by a single variable t, but a surface is parameterized by two variables. I gave you some examples also: spherical surface, cylindrical surface, some explicit surface. So hope you recall those points. Now today the first topic is area of a smooth surface. Hope you recall the meaning of smooth surface. The surface is smooth if RU, RV, the partial derivatives of R with respect to U and V are continuous, and RU cross RV is non-zero vector. Is non-zero. You know this is normal vector to the surface, and non-zero means unique vector, a unique normal vector exists at each point of the surface. Just like smoothness of this curve means R prime t is continuous and R prime t is non-zero, correct? So this ensures a continuous tangent vector to the curve at each point. So it's similar to this. Now, area of a smooth surface means you are given a smooth surface, say S. You are interested in finding the formula for area of the smooth surface. So let's see how do we get the area formula. Suppose this surface is parameterized by RUV, and the corresponding region for UV parameters in UV plane is R. Or we can say domain of the parameters UV corresponding to the surface is this region R. Okay. If we divide this region R into rectangles by choosing lines parallel to U axis and V axis, then this surface is divided into patches corresponding to these rectangles. Let's consider an elementary rectangle A, B, C, D with dimensions delta U, delta V. This rectangle. Okay. Now, if I assume coordinates of A are UV, what are coordinates of B, C, and D? U plus delta U, comma V. Coordinates of C are U plus delta U, comma V plus delta V. And coordinates of B are U, comma V plus delta V. Right? From this, dimensions are delta U, delta V. So you understand the coordinates of these four vertices ABCD. Alright. Suppose the corresponding patch on the surface is PQRS corresponding to ABCD. The patch on the surface is PQRS. PQRS respectively correspond to the points ABCD. So what is position vector of P? Because the surface is parameterized by this vector function RUV. So what is position vector of P? RUV? RUV is the position vector of P. This is position vector of Q, this is position vector of R, and this is position vector of S. Correct? P, Q, R, S. These are position vectors of these points on the surface. Now, my purpose is to approximate the area of this patch, because if I understand the area of this patch, then I can sum up all those areas to get the area of the surface. So, suppose symbolically the area of this patch is delta sigma. So, my purpose is to approximate delta sigma. How can I do that? Let us join these directly by line segments. We have a parallelogram PQRS. I can say approximately the area of this patch, or the area delta sigma of this patch, is approximately equal to area of the parallelogram PQRS. Area of the parallelogram PQRS. Okay. So how can we write the area of the parallelogram when we know the position vector for the vertices of the parallelogram? I think you know this formula. PQ vector cross R, PR, PS vector, PQ vector cross PS vector magnitude. This gives the area of this parallelogram. Am I right? Now let us see what is PQ separately to save the space and calculation. PQ vector means R U plus delta U, comma V minus R U V divided by, this I am doing from my side, delta U multiplied by delta U. What is this whole expression approximately? Partial derivative of R with respect to U clearly into delta U. Similarly, you can check yourself the vector PS is approximately RV into delta V. RV into delta V. Right? So what is this? This is approximately RU cross RV magnitude delta U delta V. These are scalars we can write outside. Correct? So area of this patch is this. If I sum up all these over the surface, what do I get? Area of the surface and the limit delta U delta V going to 0. So area of the smooth surface symbolically given by this. And what is the working formula? If you parameterize this by RV, then magnitude of double integral of magnitude of RU cross RV du. Very important formula. Keep this formula in your mind. If the surface is parameterized by UV, then its area is given by this formula. What is R? R is the domain or region of the UV parameters corresponding to the surfaces. Alright? Okay, let us do some problems using this formula. Find surface area of the sphere x square plus y square equal to, x square plus y square plus z square equal to a square. Let's find the area of this sphere. Do you know the parameterization of this? I told you in the previous lecture. What is the parameterization of the sphere in terms of theta phi, the spherical coordinates? Or we write it as phi theta, doesn't matter. What is this parameterization? K cos theta sin phi, I cap, A sin theta sin phi, j cap, and A cos phi, k cap. Right? After this, what do we need to calculate? R phi cross R theta magnitude. R phi cross R theta magnitude. Before magnitude, you need to determine this vector. How do you find it? Partially differentiate this whole expression with respect to phi, then with respect to theta, take the cross product of the two vectors. It's a matter of calculation. It's a matter of calculation. Please do it yourself, but I tell you a simple formula to remember it. Multiply this whole thing by A sin phi. This whole expression means R phi theta, or this whole expression. Multiply this whole thing by R phi theta. That is your R phi cross R theta. You can check it. After that, if you simplify the magnitude, you will get A square sin phi. Okay? R phi theta means this whole expression. I'm not writing it again. So what is surface area of the sphere? Double integral over R. R means what? The region in the theta phi plane corresponding to the spherical surface. And R phi cross R theta, I'm writing here R phi, the formula first, R phi cross R theta, d phi d theta. R is the region in the phi theta plane corresponding to the spherical surface. So phi varies from corresponding to the spherical surface. I told you earlier the variation of phi. Phi varies from 0 to pi in spherical coordinates, theta 0 to 2 pi. And this R phi cross R theta magnitude we have found as A square sin phi, d phi d theta. Now it is a simple double integral in phi and theta. You should be able to solve it yourself. The final answer is 4 pi A square. As expected, you know the surface area of the sphere is 4 pi A square. It is verified in our solution. To solve this double integral, first integrate with respect to phi, then with respect to theta. You have already practiced number of problems on double integrals, so you should be able to do it yourself. Fine. Let us do another example. Find surface area of the cylinder x square plus y square equal to a square. Z varies from 0 to h. Right circular cylinder. Base the circle, height h. You know the answer already. Find the curved surface area, remember that. We are interested in finding curved surface area of the cylinder. So again you need parameterization first. This time, what is parameterization of this cylinder? R theta z. A cos theta, I cap, A sin theta, j cap, and z k cap. So what do you need? Text. or theta cross RZ in the surface area formula. This vector unit, then its magnitude. So partially differentiate this with respect to theta, then with respect to z, then find cross product of the two vectors. We find that it is a cos theta I cap plus a sin theta z cap plus 0 k cap. Same, this component vanishes. You can verify it. So what should be the area? Double integral over R of magnitude of R theta cos RZ d theta dz. What is magnitude of this vector? A only. Theta and z for curved surface of the cylinder vary as theta varies as 0 to 2 pi, z 0 to h. Alright. And magnitude of this vector from this we can see is A. Simplify this double integral, very simple. First integrate with respect to theta, or apply upper limit minus lower limit, you get 2 pi a, then integrate with respect to z, finally you get 2 pi ah. Check it yourself. Correct? So as expected, the curved surface area of the cylinder is 2 pi ah. Okay? So it is all about parameterization of the surface. If you are able to parameterize the surface, you know the ranges of the parameters. You can apply the formula and do your calculations to get the surface area. Let's see how do we find surface area of a surface given in explicit form like this, z equal to fxy. This time what is the parameterization? xi cap plus yj cap plus fxy k cap. This also I told you in the previous lecture. What is the domain of xy? Project this surface in the xy plane. Suppose this is the given surface. If the surface is given in this format, then such a surface can always be projected in the xy plane. Suppose this is the projected region. So you have to see the limits of R from this plane region. It is the projection of this surface. Okay, this surface is z equal to fxy. This is zx is xy. Is it fine? Okay, so this is the parameterization. Xy vary in this region R. So to apply the area formula, what do you need? You need Rx cross R1, magnitude. Rx means partial derivative of R with respect to x. What is Rx from it? I cap plus 0 z cap plus fx k cap. Similarly, you can find R1. Find cross product of the two and then the magnitude. I'm writing it directly. You need to verify it. You get this expression. So what is the area formula for this surface given in explicit form? Double integral over R square root of fx square plus fy square plus 1 dx dy. Okay. For explicit surface, you can use this formula directly. So in this case, just to need to note down the fxy from the given equation of the surface. Okay. Here itself, I want to explain you one more thing. That is, area of the surface given in implicit form. Area of the surface given in implicit form, say fxyz equal to constant. This is the explicit form. Z is given in terms of xy, but here xyz are mixed, so it is implicit form. Okay. So there is a formula that can be derived. I will not go by derivation, you can see the lecture notes. Area of the surface given in implicit form is given by the double integral of magnitude of gradient of f divided by magnitude of gradient f dot k cap dx dy. Now it's important to understand what is this R. If you are able to project the surface on xy plane, able to project means when you project the surface on xy plane, it should not fold over itself. It should not fold over itself. For example, if a surface is given like this, say something like a hemisphere with this parallel to the axis, you can project it on xy plane. Then any line perpendicular to the projected region intersects the sphere, hemisphere of the surface only in one point. So this kind of projection is allowed. If you want to project the same surface on a xy plane, this is not allowed because this time the surface folds over itself. If you draw a line perpendicular to xy plane passing through the region, it intersects in 2 points. Correct? So this kind of projection is not allowed. Any line to the projected region should puncture the surface at most in 1 point. Okay? Alright, so suppose you have projected your implicit surface on xy plane, then this is the formula. Likewise, you can write formulas if you have taken the projection on yz plane or zx plane. Alright? So let's do a problem using both these, you will get the same result. Let's do a problem. But I suggest you to do all the problems using parameterization. Parameterization is an easier approach. Okay, in some problems you will find this formula easier to apply, but I suggest you to use parameterization in every problem. Okay, all problems can be done using parameterization of the surface. See this problem. Find surface area of the paraboloid z equal to x square plus y square and z varies from 0 to 4. Do you understand the shape of this? This is the shape of this paraboloid. X-axis, y-axis, z-axis. This plane, the circle is lying in the plane z equal to 4. Okay, so we are interested in finding this surface area of this paraboloid between z equal to 0 and z equal to 4. Okay. So what is fxy if I want to apply this formula? This surface is given in explicit form. So this is my fxy. Fxy is x square plus y square. So let's apply this formula. So if we apply this formula, what do we get? Fx square means 2x whole square Fy means partial derivative with respect to y, 2y whole square plus 1 dx dy. Now, from there to see the variation of x and y. Project your surface on xy plane. What do we get? Projection of the surface on xy plane. You get this? Same circle. If you project this whole surface on xy plane, what is the equation of the circle? X square plus y square equal to 4. Correct? So you can say that you need to find this double integral over this circular region, x square plus y square less than equal to 4. So because it is circular region, to simplify it, it's better to use polar coordinates. Put x equal to r cos theta, y equal to r sin theta, Jacobian is r. So how can you simplify this double integral in a simpler way? 4r square plus 1, Jacobian is r, divided theta, and r in the circle varies from 0 to 2, theta 0 to 2 pi. Okay, after that, it's easy to simplify. Answer of this double integral I'm writing for you. Please do it yourself. Pi over 6, 17 root 17 minus 1. It is 1. You should get this answer. If you get something else, let me know. Okay. Now, let's do the same problem using this one. So, write the surface in implicit form. I can write the given surface like this, fx, y, z equal to x square plus y square minus z equal to 0. Same surface in implicit form. Now to apply this formula, what do we need? First gradient f, we recall gradient formula, fxik plus fyzk plus fzk. Partial derivatives of capital F with respect to xyz as the three components. So you get 2xi plus 2yz plus plus minus k cap. What is del f dot k cap? Minus 1. So what is magnitude of this vector? Same as you are saying here. Magnitude of this vector is same as you are saying here. And what is magnitude of del f dot k cap? Plus 1. So when you put the values of these in this formula, you get the same double integral, am I right? Yes. So both approaches lead to the same double integral, okay? So of course we will get the same answer with this approach also. So we understand that how to deal with the surface given in implicit form. Okay, good. Now let us see what's next. We have learned about line integrals. Now it's the time to learn about surface integrals. Very important. Just like you learned line integrals for a scalar field and a vector field, same way, let's first see the surface integral of a scalar field capital Fx, y, z. Suppose this is defined on some smooth surface S. And how do we define its surface integral over this surface S? Let's parameterize this surface by UV. divide this surface into patches. Area of this patch is equal to delta sigma. I divide it in n patches. This is ith patch. In this patch, choose a point xi, yi, zi. Then construct the sum. Which sum? This sum. Suppose there are n patches, so I from 1 to n. Limit of this sum as it tends to infinity and delta sigma is equal to 0. If exists finitely, define surface integral of fx y z over the surface as denoted by this symbol. You can see it is analogous to the definitions of line integral and the simple integral that we learned in the beginning. Here you divided the interval AB into n subintervals. In line integral you divided the curve into subarcs and denoted the integral by this symbol. It is subinterval length, arc length, area element, correct? So you can understand the analogy between the definitions, it's easy to understand. Now the thing is that how do we calculate it? The surface is parameterized by UV. Then x is a function of UV in the parameterization, y is a function of UV, z is a function of UV. D sigma in terms of UV, you already know, it is magnitude of RU cross RV. When the surface is parameterized by UV. And you can see the limits of UV in the UV plane in the region corresponding to the surface. Okay? So this is the working formula for surface integral. Is it fine? We'll do a problem on it, you will understand. But first, note down this formula. Surface integral of the scalar field fxyz over the surfaces is given by this formula. What about surface integral of a vector field? Surface integral of the vector field fxyz over the surfaces. Denoted by this symbol. How to solve it? Actually, surface integral of the vector field f is the surface integral of the normal component of f over the surfaces. Now it is a scalar quantity, you can use the same approach to solve it. Once you take the dot product of these two vectors, you have a scalar field, right? And using the same, sorry, here you don't have vector, it's scalar. Yes, but it is a vector field, okay? So I was saying that when you consider dot product of these two, what do you get? A scalar field. So you can apply the same approach to solve it. Alright? If you recall from line integrals of the vector field f, what did you define there? F dot p cap ds along the curve C and f dot n cap ds along the curve C. Correct? Because now you are on a surface, so this tangent vector doesn't make sense because we consider tangent plane, right? Makes sense, but you know at a point of the surface, tangent vector is not unique. There are infinitely many tangent vectors. So we don't consider this, we consider this one. Normal vector is unique to a surface. Okay? And also, which side we should consider the direction of n cap. Conventionally, it is It is opposite to the concave side of the surface. Here I would like to clarify one more point regarding this line integral. If you recall chapter 13, to any curve C we define two vectors t cap and n cap. Here n cap is naturally towards the concave side. But when we define this line integral, we consider it in the opposite direction. Reason is that we are interested in finding outward flux. So there is a physical interpretation, that's why we consider it in the opposite direction. So okay, you can calculate n cap using the previous formula, but multiply it by -1 in your calculations, okay? Okay, so here n cap is opposite to the concave side of the surface by convention, because here also it represents outward flux across the surfaces. Note down this formula. Outward flux across the surfaces is given by this double integral, okay? And you should also note down a simplified formula for it. If the surface is parameterized by RUV, this surface, then what is n cap? You know RU cross RV is a vector normal to the surface. N cap means divide this vector by its magnitude. So if you do so and change everything in terms of UV, then what do you get? F naturally changes to a function of UV. I'm interested in knowing what happens here. N cap is this. What is this sigma? This sigma, you know, RU cross RV magnitude, du dv. So when you multiply n cap with this thing, what is left? F dot RU cross RV vector. You need not to deal with the magnitude. That is the advantage. For outward flux, you need not to deal with the magnitude of RU cross RV. So it is a simplified formula for the problems. You can make a note of it. Okay. Now let's do a problem on surface integral. That will help you to understand these formulas. Integrate the function 4x square plus 4y square plus 1 square root of 4x square plus 4y square plus 1 over the paraboloid, over the curved surface of the paraboloid z equal to x square plus y square, 0 less than equal to z less than equal to 2. This is the surface given true. Now how to do it? That's the point. Instead, let's denote it by z or by fxy, because you have xy here. Okay. So how to find surface integral of this function or the scalar field over the given surface of paraboloid? Write your formula first. What do you need in the calculations? What do you need in the calculations? Surface integral is given by, if you are parameterizing your surface by, okay, let me avoid this, so this will create confusion. Actually, we are interested in parameterization of this surface, right? So I'm writing the formula first. It is given by fx uv y uv z uv. If you are parameterizing the surface by uv over r, and v sigma is replaced by magnitude of RU cross RV du dv. In this case, what is your surface? The paraboloid. Okay. This is a given surface. What is this circle? Or what is the plane of the circle z equal to 2? Alright. Because this is an explicit surface, we can assume it of xy. We can parameterize in terms of xy. If we parameterize in terms of xy, what do you have? This formula changes to what? This is your capital F actually. Notations. For explicit surface, we usually denoted this term by small f xy. That's why I removed that from the place. Okay? Alright. Now, what is capital F in terms of xy? 4x squared plus 4y squared plus 1. What is RU cross RV magnitude? For explicit surface, this is Rx cross Ry magnitude in fact. So this you know is given by fx squared plus fy squared plus 1. Then dx dy. This region belongs to the domain of xy corresponding to the given surface. So project the surface on xy plane. You get which circle? Same circle. This circle. X squared plus y squared equal to 2. Okay, so I can say that this region is given by x squared plus y squared less than or equal to 2. Now from this fxy, what is fx? 2x, fy 2y. This is 2x whole square, 2y whole square plus 1 square root. Same thing as we are saying here. So what is that? 4x squared plus 4y squared plus 1 dx dy. Okay. So what are the variations of xy? Instead of writing the variations of xy, it's better to change it in polar coordinates. You know it's circular region. It's easy to deal in polar coordinates. Put x equal to r cos theta, y equal to r sin theta, and simplify it. So for this circle, r varies from 0 to root 2, theta 0 to 2 pi, and this becomes 4r square plus 1, dx dy changes to Jacobian, that is r, dr theta. Now you can see it's a simple double integral. You can simplify it and reach to the answer. Its answer should be 10 pi. Verify it. Its answer should be 10 pi. Okay, so it's all about parameterization of the given surface and applying the correct formula. You can easily do these problems. Now let us see surface integral of a vector field. Find the outward flux of the vector field 4xi cap minus 2y squared j cap plus z square k cap. Across the curved surface of the cylinder, x square plus y square equal to 16, z in the range 0 to 3. Okay. So we need to find outer flux across this curved surface of the cylinder. How this cylinder looks like. X-axis, y-axis, z-axis. Okay, so around this curved surface, we are interested in finding across this curved surface, we need to find the outer flux of F. So what is the formula for outer flux? What is the formula for outer flux? It is F dot RU cross RV, the surface is parameterized by UV, du dv. What is the surface here? Cylindrical surface, and you know the parameterization of cylindrical surface, it is R theta z. So you will write here R theta cross RZ d theta dz. R is the region, corresponding region in theta z prime. Alright, so what do we need here? F on the surface of the cylinder and R theta cross RZ. What is F on the surface of the cylinder? What is parameterization of cylinder? Let's write it for this particular cylinder. R theta z is 4 cos theta v cap, 4 sin theta z cap, plus z k cap. This is the parameterization of the cylindrical surface. Okay. So what is R theta cross RZ from it? We've done it earlier. It's 4 cos theta cap plus 4 sin theta z cap plus 0k. Okay. Now we need F on the surface of the cylinder. What is F on the surface of the cylinder? Put x equal to 4 cos theta, y equal to 4 sin theta. So you get 4 cos theta I cap minus 16 sin square theta, no, 16 into 2, 32. 32 sin square theta z cap plus z square k cap. What is the dot product of this and this vector? Write that. What is the dot product of these two vectors? Write that here and then apply the limits of theta and z in this double integral. You know, for this cylindrical surface, theta goes from 0 to 2 pi, z goes from 0 to 3. It is given here. So just do the dot product of these two vectors and write that here. Solve this double integral. I hope you will do it yourself comfortably. I'm writing the final answer. It is 192 pounds. Verify it. It's an exercise for you. One more thing, how do you know this vector is pointing outwards? This gives normal vector to the surface. It could be this inner side, it could be outer side. From this order you don't know this thing, okay? So how to check it? Choose a point on the surface. It is a very important point. Please notice it. Choose any particular point on the surface. Say I am choosing a point on x-axis and the point is 1, 0, 0. What is this circle? No, it's 4, 0, 0. The cylinder cuts x-axis in which point? 4, 0, 0. Right? Yes. So, at 4, 0, 0, what is the value of this vector? or this point corresponds to theta equal to 0. So if you put theta equal to 0, what do you get? At theta equal to 0, what is your vector? It is 4 I cap. 4 I cap points in outwards direction to the cylindrical surface. Am I right? Yes, it points in the outward direction. So it's fine. In case it is pointing inward, multiply the whole vector by -1 to find outward flux. Okay? Alright, now in this chapter, what is left? Stokes theorem and Bartolomew's theorem. Let's do it in the next lecture. So, after learning all these concepts, you need to practice problems. Hope you will do all the problems comfortably. In case you face difficulties, you can ask me. You can drop an email to me, or you can ask in the YouTube comment section. Me or somebody else will reply there. Okay? So let's meet in the next lecture. Thank you.